Okay, hello everyone. We'll get started. I'm Nina with Radius, and it's really good to see everyone here. So we have teams here working on different blockchain scaling solutions, and we're really excited to dig into what they have been working on currently. So as far as the agenda, if you all got an NFC card, you can just tap it into your phone, and then it will have our timetable on it. And after this event, the content there will be updated. So please check on that later. So the first session will have 3 speakers, Starkware, Mina, and Anoma, followed by a panel discussion with them. And then we'll have a break for 5 minutes or 10 minutes, as we're pretty tight on time. And the second session will be the same format, but we'll have 4 speakers, Radius, Osmosis, Saga, and Flashbots. And then we'll have some Korean traditional snacks towards the end, so if you can all hang on till then. And then lastly, after the last panel discussion, we'll have the rest of the time for networking, and it'll be around for 45 minutes. So with that said, we'll get started. The first speaker will be Ariel, who's a product manager from Starkware. And he'll be speaking about Starkware's Cairo 1.0 and Sierra. Please welcome him.
Hello. Hi. So I'm Ariel, product manager in Starkware. And today I'll be talking about Cairo 1 and Sierra, but actually mostly Sierra. Okay, so let's start with a brief introduction of what's Cairo. So basically, Cairo is the most overloaded word in the Starknet ecosystem. We're using it for a lot of actually different components. And that guy is me telling you how Cairo is actually everything. So essentially 2 to 3 years ago, we've developed in Starkware the Cairo VM, which is a CPU architecture which is friendly for proving. Basically, we have an instruction set where every instruction has some compact algebraic representation. If I have a jump here instruction, I can efficiently say how it affects the memory and registers in an algebraic manner, and that's how I can create efficient proofs for programs that are written in this instruction set. So that's the Cairo VM, and that's the big advantage that it gives us. It is optimized for proving. But above the Cairo VM and its instruction set, the Cairo Assembly, we had Cairo 0, now we have Cairo 1, which are higher level languages. And actually we're using Cairo for everything. The VM, the instruction set, Cairo 0, Cairo 1, everything is Cairo. Okay. So in the good old days, we had the Cairo Assembly, which is, like I mentioned, the instruction set for the Cairo VM. And we had Cairo 0. So if there are any brave developers here who are experienced with Cairo 0, you're familiar with this syntax. So while developers wrote complex and meaningful business logic in Cairo 0, there was still a lot to improve. So just to mention a few of the known pain points, you couldn't, for example, override variables. There were no features that are well known in modern languages, type systems, arrays, inheritance, that sort of stuff. Okay, so Cairo 1 came to fix all that. And Cairo 1 is modeled in the spirit of Rust. So you have a lot of features that the Rust community very much appreciates. You have INA matchings, you have traits and impels, you have generics. These are stuff that are pretty much unimaginable in the world of Cairo 1. Okay, so this is Cairo 1, but actually the focus of this talk is going to be an intermediate layer, a new intermediate layer between Cairo 1 and the eventual Cairo Assembly, which I've mentioned previously. So Cairo 1 compiles down to Sierra, which stands for Safe Intermediate Representation, and we'll discuss shortly in what sense is it safe. And the Sierra then compiles to Cairo Assembly or CASM. Okay, so Sierra, Safe Intermediate Representation. This representation is not unique. You could probably move letters around. Okay, so the process now is that devs write in Cairo 1, they compile it locally, they get Sierra code, and they submit it to the network. This is different from the previous world where users would have sent Cairo Assembly directly to the network. So we sort of have a separating layer between the lowest level that gets proven and user code. And we'll discuss why it's important. Okay, so the structure of Sierra is relatively straightforward. It has a pretty small core and a collection of what we call libfuncs, basically a set of logical operations, arithmetic operations are libfuncs, jumps are control flows are libfuncs, and the Sierra program is essentially a sequence of libfuncs application. So a very simple intermediate representation. Okay, and the most important property about Sierra is that it compiles down to Cairo Assembly. Actually, the Cairo VM and the Cairo Assembly remain pretty much unchanged since their inception 2 to 3 years ago. So Cairo 1 is operating and Sierra operating on a layer above that. Okay, so why do we need Sierra? Why do we need CASM? Why do I bother telling you about this stuff? So CASM is here for proving. That's what we used for creating efficient proofs. To be able to efficiently prove the execution of a program, I need it to be represented as a sequence of Cairo instructions. So as long as I want to prove efficiently, I need Cairo Assembly. Okay, so why Sierra? Why not work as we did before directly with the Cairo Assembly? So to answer that question, I need to get into what exactly I'm expecting from those proofs. And there are basically 2 very important properties. Okay, the first is pretty straightforward. That's soundness. I don't want the prover to be able to cheat and prove incorrect things. But the safety in Sierra is actually more about completeness. I want to be able to prove every correct computation. I don't want it to be the case that certain transactions are not provable. And the blockchain space actually inserts some complexity here. Let's consider a simple example where an Ethereum transaction gets reverted due to division by 0. So in the Ethereum world, that's pretty straightforward. The validator takes the transaction, includes it in a block, marks that it was reverted, and charges fee corresponding to the gas up to the point of failure, up to the point of division by 0. But with Cairo, when I actually care about proving things, if I have a Cairo assembly instruction, which is a division by 0, I cannot prove it. If anywhere in the execution flow you hit this instruction, this is unprovable because this is incorrect. I can't do it, so I can't prove it. This is actually by design, but in the blockchain context, that's a problem because now I can put this transaction in a block. Okay, so let's talk about denial of service attacks and how they're connected to unsatisfiable constraints. And we'll see here a more complex example of the division by 0 I've just mentioned. So this is Cairo 0 code for finding an element in an array. Basically, this function gets a pointer to an array, and it should return a pointer to the requested element in the array. So it gets a pointer to an array and the key to be found. So this code may look a little bit weird from a first glance. You see on line 4 that I define a local variable called index, and in line 8, just before the end, I somehow magically expect the requested element to be in that index, but there is no looping, there is no iteration. Why would I expect this? From a first glance, this code looks very silly. So the magic is actually in line 5 in the curly brackets, which I've omitted for brevity. So in Cairo 0, we had the concept of hints. Basically, since I did not substitute anything to the index variable, it is unconstrained. The prover has complete freedom of what to substitute in it. So he can, outside the context of Cairo, outside the context of the Cairo VM, actually look for the element in the array with a regular loop in whatever language he prefers, and then substitute the result. So this is the hint. And if the element is there, he can substitute the correct index and then continue to proving the execution. So basically, this magic sort of allowed us a constant time finding an element in the array. More precisely, it's a non-deterministic constant time, but let's ignore it. Non-deterministic log space. Okay, but what if the element is not in the array? If the element is not in the array, regardless of what the prover substitute in index, the assertion in line 8 will fail. The element is not there, nothing I can do about it. And this means that this code won't be provable. There are certain parameters I can call find element with for which the execution will not be provable. Again, it's not a bug, it's by design. I cannot pass the assertion, so I wouldn't want to prove it. But in the context of Starknet, this is a problem. And I'll say clearly why. So again, we had the happy flow, the element is there, the prover gives the right hint, we're happy. But in the unhappy flow, nothing I can do will cause this code to run successfully. And this introduces a very critical denial of service attack on the chain, which is actually pretty straightforward. All I need to do is define a very large array, look for an element that is not there. The sequencer will have to look for it. He will have to try to find the index, even if it's outside the context of running Cairo Assembly. He needs to know what to substitute for that index variable we've seen. He will figure out it's not there, and then he cannot proceed. Unlike the validator in the division by 0 example, I can't include the transaction in a block because I can't prove it. And if I can't include it in a block, I can't get paid. So that's a very big problem. I did a lot of work. I iterated through a very large array. I get no money. I'm very sad. Okay. So that's where Sierra kicks in. With Sierra, find element is actually a libfunc. So again, it compiles down to Cairo Assembly, but it will have to compile down to some different Cairo Assembly. We're going to have to take care of the problem. So in the happy flow, nothing is going to change. We're still going to use the same code as before. We're going to utilize the power of hints. Someone can magically give me the hint. But in the unhappy flow, I must gracefully handle failures. I need in Cairo to iterate over the entire array and convince myself that the element is not there. This is replacing the assertion we've seen before. So now I can sort of fail gracefully, and now I can prove this and charge money for it. And this is actually the key idea behind Sierra. As long as the compiler does its job correctly, the compiler from Sierra to Cairo Assembly, then we can be sure that only safe CASM is generated. And safe in the sense that for every possible set of inputs, the computation is provable. And this is a property that is very critical in the blockchain space because, like we've seen, we need to be able to charge money for reverted transactions. Okay, so that's the critical thing to think about when designing new libfuncs in Sierra, and this is the important safety guarantee we get from it. So I don't think I have a lot of time, so I will very briefly mention one other benefit we get from Sierra. So I'll ignore gas metering for now, but I will mention separating the execution and prover environments. If we need Cairo Assembly just for proving, then why should the sequencer care about it? The sequencer wants to produce a block as fast as it can. If it can do it in a few seconds less, that's critical for our throughput. So why compile it down to QASM, which is only important for proving? So this is an actual project which is ongoing, Sierra to MLIR. MLIR is a well-known intermediate representation used by many modern compilers. And what you could do is instead translate Sierra to MLIR and then run MLIR on some native architecture. So the sequencer wouldn't necessarily have to go through Cairo Assembly or the Cairo VM. This will only happen on the prover side. There are certain properties about Sierra that make it, let's say, friendly to this translation. There are a few things we can make use of when translating to MLIR and then native architecture. But let's ignore those for now. So there are still a lot of improvements coming to both Cairo 1 and Sierra, and I urge you to basically join the effort, see the Cairo book, see the Starknet docs, join our Cairo 1 Discord, and start writing, and feel free to take part in this. That's it. Thank you. Any questions? No? Okay. Feel free to find me afterwards. Thank you.